Heat transfer is the exchange of thermal energy between physical systems, depending on the temperature and pressure, by dissipating heat. The fundamental modes of heat transfer are conduction or diffusion, convection and radiation. Heat transfer always occurs from a region of high temperature to another region of lower temperature. Heat transfer changes the internal energy of both systems involved according to the first law of thermodynamics. The second law of thermodynamics defines the concept of thermodynamic entropy by measurable heat transfer. Thermal equilibrium is reached when all involved bodies and the surroundings reach the same temperature. Thermal expansion is the tendency of matter to change in volume in response to a change in temperature. Overview. Heat as defined in physics is the transfer of thermal energy across a well-defined boundary around a thermodynamic system. The thermodynamic free energy is the amount of work that a thermodynamic system can perform. Enthalpy is a thermodynamic potential, designated by the letter H. That is the sum of the internal energy of the system plus the product of pressure and volume. Joule is a unit to quantify energy, work, or the amount of heat. Heat transfer is a process function, as opposed to functions of state. Therefore, the amount of heat transferred in a thermodynamic process that changes the state of a system depends on how that process occurs, not only the net difference between the initial and final states of the process. Thermodynamic and mechanical heat transfer is calculated with the heat transfer coefficient, the proportionality between the heat flux and the thermodynamic driving force for the flow of heat. Heat flux is a quantitative, vectorial representation of the heat flow through a surface. In engineering contexts, the term heat is taken as synonymous to thermal energy. This usage has its origin in the historical interpretation of heat as a fluid that can be transferred by various causes, and that is also common in the language of laymen in everyday life. The transport equations for thermal energy, mechanical momentum, and mass transfer are similar, and analogies among these three transport processes have been developed to facilitate prediction of conversion from any one to the others. Thermal engineering concerns the generation, use, conversion, and exchange of heat transfer. As such, heat transfer is involved in almost every sector of the economy. Heat transfer is classified into various mechanisms, such as thermal conduction, thermal convection, thermal radiation, and transfer of energy by phase changes. Mechanisms. The fundamental modes of heat transfer. Advection. Advection is the transport mechanism of a fluid substance or conserved property from one location to another, depending on motion and momentum. Conduction or diffusion, the transfer of energy between objects that are in physical contact. Thermal conductivity is the property of a material to conduct heat and evaluated primarily in terms of Fourier's law for heat conduction. Convection, the transfer of energy between an object and its environment, due to fluid motion. The average temperature is a reference for evaluating properties related to convective heat transfer. Radiation, the transfer of energy from the movement of charged particles within atoms is converted to electromagnetic radiation. Advection, by transferring matter, energy, including thermal energy, is moved by the physical transfer of a hot or cold object from one place to another. This can be as simple as placing hot water in a bottle and heating a bed, or the movement of an iceberg in changing ocean currents. A practical example is thermal hydraulics. This can be described by the formula, where Q is heat flux, ρ is density, is heat capacity at constant pressure, delta T is the change in temperature, is velocity. Conduction on a microscopic scale. Heat conduction occurs as hot, rapidly moving or vibrating atoms and molecules interact with neighboring atoms and molecules, transferring some of their energy to these neighboring particles. In other words, heat is transferred by conduction when adjacent atoms vibrate against one another, or as electrons move from one atom to another. Conduction is the most significant means of heat transfer within a solid or between solid objects in thermal contact. fluids, especially gases, are less conductive. Thermal contact conductance is the study of heat conduction between solid bodies in contact. Steady-state conduction is a form of conduction that happens when the temperature difference driving the conduction is constant, so that after an equilibration time, the spatial distribution of temperatures in the conducting object does not change any further. In steady-state conduction, the amount of heat entering a section is equal to amount of heat coming out. Transient conduction occurs when the temperature within an object changes as a function of time. Analysis of transient systems is more complex and often calls for the application of approximation theories or numerical analysis by computer. Convection. The flow of fluid may be forced by external processes, or sometimes by buoyancy forces caused when thermal energy expands the fluid, thus influencing its own transfer. The latter process is often called natural convection. All convective processes also move heat partly by diffusion, as well. Another form of convection is forced convection. In this case, the fluid is forced to flow by use of a pump, fan or other mechanical means. Convective heat transfer, or convection, is the transfer of heat from one place to another by the movement of fluids. A process that is essentially the transfer of heat via mass transfer. Bulk motion of fluid enhances heat transfer in many physical situations, such as between a solid surface and the fluid. Convection is usually the dominant form of heat transfer in liquids and gases, although sometimes discussed as a third method of heat transfer. Convection is usually used to describe the combined effects of heat conduction within the fluid and heat transference by bulk fluid flow streaming. The process of transport by fluid streaming is known as advection, but pure advection is a term that is generally associated only with mass transport in fluids, such as advection of pebbles in a river. In the case of heat transfer in fluids, where transport by advection in a fluid is always also accompanied by transport via heat diffusion, the process of heat convection is understood to refer to the sum of heat transport by advection and diffusion. Conduction. Free, or natural convection occurs when bulk fluid motions are caused by buoyancy forces that result from density variations due to variations of temperature in the fluid. Forced convection is a term used when the streams and currents in the fluid are induced by external means, such as fans, stirrers, and pumps, creating an artificially induced convection current. Convection cooling. Convective cooling is sometimes described as Newton's law of cooling. The rate of heat loss of a body is proportional to the temperature difference between the body and its surroundings. However, by definition, the validity of Newton's law of cooling requires that the rate of heat loss from convection be a linear function of the temperature difference that drives heat transfer, and in convective cooling this is sometimes not the case. In general, convection is not linearly dependent on temperature gradients, and in some cases is strongly nonlinear. In these cases, Newton's law does not apply. Convection versus conduction in a body of fluid that is heated from underneath its container. Conduction and convection can be considered to compete for dominance. If heat conduction is too great, fluid moving down by convection is heated by conduction so fast that its downward movement will be stopped due to its buoyancy, while fluid moving up by convection is cooled by conduction so fast that its driving buoyancy will diminish. On the other hand, if heat conduction is very low, a large temperature gradient may be formed and convection might be very strong. The Rayleigh number. T is the temperature, nu is the kinematic viscosity, and L is characteristic length. The Rayleigh number can be understood as the ratio between the rate of heat transfer by convection to the rate of heat transfer by conduction, or, equivalently, the ratio between the corresponding timescales, up to a numerical factor. This can be seen as follows, where all calculations are up to numerical factors depending on the geometry of the system. The buoyancy force driving the convection is roughly, so the corresponding pressure is roughly. In steady state, this is cancelled by the shear stress due to viscosity, and therefore roughly equals, where v is the typical fluid velocity due to convection and the order of its timescale. The conduction timescale, on the other hand, is of the order of. Convection occurs when the Rayleigh number is above 1000–2000. Radiation. Thermal radiation occurs through a vacuum or any transparent medium. It is the transfer of energy by means of photons in electromagnetic waves governed by the same laws. Earth's radiation balance depends on the incoming and the outgoing thermal radiation. Earth's energy budget. Anthropogenic perturbations in the climate system are responsible for a positive radiative forcing which reduces the net long-wave radiation loss to space. Thermal radiation is energy emitted by matter as electromagnetic waves. Due to the pool of thermal energy in all matter with a temperature above absolute zero, thermal radiation propagates without the presence of matter through the vacuum of space. Thermal radiation is a direct result of the random movements of atoms and molecules in matter. Since these atoms and molecules are composed of charged particles, their movement results in the emission of electromagnetic radiation, which carries energy away from the surface. The Stefan-Boltzmann equation, which describes the rate of transfer of radiant energy, is as follows for an object in a vacuum. For radiative transfer between two objects, the equation is as follows, where Q is the heat flux, epsilon is the emissivity, sigma is the Stefan-Boltzmann constant, and T is the absolute temperature. Radiation is typically only important for very hot objects, or for objects with a large temperature difference. Radiation from the sun, or solar radiation, can be harvested for heat and power. Unlike conductive and convective forms of heat transfer, thermal radiation can be concentrated in a small spot by using reflecting mirrors, which is exploited in concentrating solar power generation. For example, the sunlight reflected from mirrors heats the PS10 solar power tower, and during the day it can heat water to 285 degrees Celsius. Phase transition. Phase transition or phase change takes place in a thermodynamic system from one phase or state of matter to another one by heat transfer. Phase change examples are the melting of ice or the boiling of water. The Mason equation explains the growth of a water droplet based on the effects of heat transport on evaporation and condensation. Types of phase transition occurring in the four fundamental states of matter include solid deposition, freezing and solid-to-solid transformation, gas boiling, evaporation, recombination, deionization, and sublimation, liquid condensation and melting, fusion, plasma ionization. Boiling. The boiling point of a substance is the temperature at which the vapor pressure of the liquid equals the pressure surrounding the liquid, and the liquid evaporates, resulting in an abrupt change in vapor volume. Saturation temperature means boiling point. The saturation temperature is the temperature for a corresponding saturation pressure at which a liquid boils into its vapor phase. The liquid can be said to be saturated with thermal energy. Any addition of thermal energy results in a phase transition. At standard atmospheric pressure and low temperatures, no boiling occurs and the heat transfer rate is controlled by the usual single-phase mechanisms. As the surface temperature is increased, local boiling occurs and vapor bubbles nucleate, grow into the surrounding cooler fluid, and collapse. This is subcooled nucleate boiling, and is a very efficient heat transfer mechanism. At high bubble generation rates, the bubbles begin to interfere and the heat flux no longer increases rapidly with surface temperature. At similar standard atmospheric pressure and high temperatures, the hydrodynamically quieter regime of film boiling is reached. Heat fluxes across the stable vapor layers are low, but rise slowly with temperature. Any contact between fluid and the surface that may be seen probably leads to the extremely rapid nucleation of a fresh vapor layer. At higher temperatures still, a maximum in the heat flux is reached. The Leidenfrost effect demonstrates how nuclear boiling slows heat transfer due to gas bubbles on the heater's surface. Condensation. Condensation occurs when a vapor is cooled and changes its phase to a liquid. During condensation, the latent heat of vaporization must be released. The amount of the heat is the same as that absorbed during vaporization at the same fluid pressure. There are several types of condensation. Homogeneous condensation, as during a formation of fog. Condensation in direct contact with subcooled liquid. Condensation on direct contact with a cooling wall of a heat exchanger. This is the most common mode used in industry. Film-wise condensation is when a liquid film is formed on the subcooled surface, and usually occurs when the liquid wets the surface. Drop-wise condensation is when liquid drops are formed on the subcooled surface, and usually occurs when the liquid does not wet the surface. Drop-wise condensation is difficult to sustain reliably, therefore, industrial equipment is normally designed to operate in film-wise condensation mode. Melting. Melting is a physical process that results in the phase transition of a substance from a solid to a liquid. The internal energy of a substance is increased, typically by the application of heat or pressure, resulting in a rise of its temperature to the melting point, at which the ordering of ionic or molecular entities in the solid breaks down to a less ordered state and the solid liquefies. An object that has melted completely is molten. Substances in the molten state generally have reduced viscosity with elevated temperature. An exception to this maxim is the element sulfur, whose viscosity increases to a point due to polymerization and then decreases with higher temperatures in its molten state. Modeling approaches. Heat transfer can be modeled in the following ways. Climate models. Climate models study the radiant heat transfer by using quantitative methods to simulate the interactions of the atmosphere, oceans, land surface, and ice. Heat equation. The heat equation is an important partial differential equation that describes the distribution of heat in a given region over time. In some cases, exact solutions of the equation are available. In other cases, the equation must be solved numerically using computational methods. Lump system analysis. Lump system analysis often reduces the complexity of the equations to one first-order linear differential equation, in which case heating and cooling are described by a simple exponential solution, often referred to as Newton's law of cooling. System analysis by the lump capacitance model is a common approximation in transient conduction that may be used whenever heat conduction within an object is much faster than heat conduction across the boundary of the object. This is a method of approximation that reduces one aspect of the transient conduction system, that within the object, to an equivalent steady state system. That is, the method assumes that the temperature within the object is completely uniform, although its value may be changing in time. In this method, the ratio of the conductive heat resistance within the object to the convective heat transfer resistance across the object's boundary, known as the Biot number, is calculated. For small Biot numbers, the approximation of spatially uniform temperature within the object can be used. It can be presumed that heat transferred into the object has time to uniformly distribute itself, due to the lower resistance to doing so, as compared with the resistance to heat entering the object.